morning, everyone. So it's 9 a.m. and we can start. Again, the exam will be on Thursday, right? Again, as usual, we will start earlier at 8:40. I sent you an email about that, right? So with all the information. I will contact today extra time students, right, who need extra time to do the exam. Okay, so back to the work. So today, the main goal of today's class, magnetic force. But before we dive into the magnetic force, we need to discuss a few slides from the previous lecture. It will take us maybe like 5 minutes, okay? All right, so, I need to press on my slides. Okay, now it should work. Okay, so we need to introduce a solenoid because from this point right now we are in the world of magnetism, and almost every class we are going to use uniform magnetic fields, but we still don't know which device, which object can produce and give us a uniform magnetic field. So that's what solenoid does for us. So what is solenoid? Basically, if you take any cylindrical surface, right, like I took this marker and piece of wire, and if you wrap it, this wire, around this marker, okay, and send a current through this, you will get, so basically I build a solenoid. I build a solenoid. Not the best one, but it will be a solenoid, right? Okay, so, and of course here, I took from the stock room and I keep it because I need it almost every semester, right? So here's another solenoid, right? So how come that it gives us a uniform magnetic field? Well, so let's just follow steps that we have to make in order to build a solenoid. All right, so if you have just a straight piece of wire, right, like this, of course you will see you will have these magnetic field lines, right? Circles, and we know how we can find directions of these magnetic field lines, right? Outline your thumb in the direction of the current, and your curl fingers gives you direction of the magnetic field lines. Somebody's mic is on. Okay. Right. So now if we, out of this straight wire, let's say we create a small loop, right? Small loop. And in this case, if we create the loop, if we look at the magnetic field lines, you're going to have something like this. All right, so these are magnetic field lines if you have a loop. All right, and now if you, right, start adding more and more loops, identical loops, to the first one. If you take another loop, put it next to the first one, then another one, and so on. If you create a few thousands of these loops, in that case, all these magnetic field lines you see, these and over here, right, these, they will be also all kind of squeezed into the inside of these loops. And as a result, you will end up with a picture like this, right? So we have, you see these loops, right? So here current flows out of the board, here below into the board, right? So basically these are loops. And if you stay away from the edges, you see near the edges, lines get spread, magnetic field lines. As a result, magnetic field start changes. But if you stay deep inside of the solenoid, you're going to have uniform magnetic field. You see density of lines the same, direction of the magnetic field lines again the same. So inside of the solenoid, we have uniform magnetic field, right? So this is the first system which can give us a uniform magnetic field, right? And magnetic field just outside of the solenoid is 0. It reminds lots of similarities between a parallel plate capacitor and a solenoid. But of course, parallel plate capacitor, it's an object in the world of electricity, right? And a solenoid in the world of magnetism. Again, you remember, capacitor gave us uniform electric field, and electric field just outside of the capacitor was 0. Here the same, similar, not the same, similar. Magnetic field inside is uniform, outside magnetic field is 0. Lots of similarities between a parallel plate capacitor and a solenoid. Right. Okay, I took this picture from the book. Right, so if you take, for example, some oil or some other liquid, right, and spray like iron filings on the surface, right, and put a solenoid inside, it will create a picture like this. Why? Because each that pieces of metal, right, it's basically like a small compass needle, right? And of course, they will respond on the presence of the magnetic field, and of course, they will orient themselves along magnetic field lines. And as a result, you can see that, yeah, magnetic field lines inside, you see more or less density the same, so uniform. Outside, right outside, it's just a chaos, right? There are no any directions. It means that magnetic field over here most likely 0, right? And you see magnetic field lines outside, kind of spreading. Okay, so now, of course, the next logical question, yeah, we have magnetic field inside, and it's uniform. What's the expression? What's the formula to calculate magnetic field inside of a solenoid? And here is very busy slide. A couple of years ago, I used to go through this in the lecture, but every time when I did this, I felt very uncomfortable because it's too much for a lecture where we use PowerPoint presentation, right? So at some point, I stopped presenting it, and I started assigning it as a take-home quiz. But since this semester every quiz is a take-home quiz, so that will be basically your quiz number 5. Right? So what do you have to do? Just take a blank piece of paper, draw a solenoid diagram like this, right? And you need to derive the formula for the magnetic field inside of the solenoid using Ampere's law. You can use any book you want, our book or something else, or other books, or you can use my slides. This will be posted. It's already posted. All right. So using Ampere's law, you need to, again, as I said, draw a solenoid, draw an Amperean loop, show all these vectors B and ds for each part of the loop, because you will have to split integral into 4 integrals, justify that integral is 0, that integral is 0, this one is not 0, and then derive this formula. Very simple. I just want you to do this at home by yourself, right? On a blank piece of paper. And after this lecture, I need to create quiz number 5 in grade scope. So that will be your quiz 5. All right. So from now on, we will use this formula for magnetic field inside of the solenoid. Universal constant mu naught. Then n, it's a number of loops per unit length in the solenoid, because usually solenoid has several thousands of loops, right? So it's more convenient to give a sort of like a density of loops, number of loops, n small, number of loops per unit millimeter, for example, per millimeter. Right? And I is the current through one of these loops. So we're going to use this formula quite often. Right. Okay, so that's your quiz. It shouldn't be complicated. Right. Then applications. Where do we use solenoids? MRI machine. Why does it have this cylindrical shape? Because it's basically it is a solenoid. It is a solenoid. So a person is just shoved into the inside of the solenoid. You see this picture, right? So solenoid and person is inside, exposed to a very large magnetic field. 1 Tesla, you remember that 1 Tesla is a strong, very strong magnetic field. And in order to achieve that magnetic field, current through this solenoid must be very large. As a result, you need to keep this device at low temperature. Of course, not the person, the solenoid, at low temperature. And that's one of those few machines where liquid helium is used. Right? Liquid helium is kind of rare and expensive, right? Last time I used it a lot, like 8 years ago, and it cost like $12 per liter. And it gets evaporated very, very fast, right? So it's kind of expensive to run an equipment with liquid helium. But because this machine is so good, yeah, industry sort of accepts a device where liquid helium is used. If you come up with a new idea or a new piece of equipment where liquid helium is used and try to sell it to industry, chances that it will be accepted minuscule. No one is going to work with an equipment where liquid helium must be used. Liquid nitrogen, okay, but liquid helium, too expensive to run. But since it is so good, all right, difficult to replace, so. Okay, so it's one of the applications where solenoids are used. But of course, there are plenty of other applications. Okay, so it's enough about that. Basically, that's this slide. Those slides are from the previous lecture. And now, before we move to the main subject of today's class, let's discuss this. I don't know how to call it, sort of like a philosophical, historical digression. Let's recall Oersted Experiment, what he did. At the beginning of, I think, 19th century, right? Yeah, beginning of 19th century, right? Hans Oersted, he did this experiment according to the legend, historical legend, right? But of course, legends can be twisted, changed slightly. But according to the legend, he was demonstrating something using strong current through the wire. And again, according to the legend, there was a compass needle not that far away. And he noticed that whenever he would turn the current on, current through the wire, the compass needle would respond, change its position, orientation, not position, orientation, right? And when he would turn the current off, compass would change orientation again. Okay, it sounds like banal, trivial, right, for us, but still, lots of people believe that it's probably one of the most important experiments ever done. How come? What's so important about this? Sounds like trivial experiment, simple experiment. And the explanation is this. Back then, again, beginning of 19th century, just the Napoleon Wars were just over, right? People believed, researchers believed, that here there is a world of electricity, its own independent world of electricity. Some people, some researchers did their work, research in that world of electricity. And here there was a world of magnetism. Again, some people did their work in the world of magnetism. And they believed, people believed, right, that these are two independent worlds, world of electricity, world of magnetism, right? And what do we have here? What do we observe? So we have a current, a pure representative of the world of electricity. Compass needle, a pure representative of the, from the world of magnetism. And they interact. So it means that these two worlds of electricity and magnetism, they are not isolated. They are not independent. They overlap somehow. So it was first experiment where people noticed, okay, these two worlds not independent. They overlap, and of course they didn't know how deep overlapping was. Of course, the overlapping is very, very deep. Right now, we know that it's impossible to separate the world of electricity from the world of magnetism. They're inseparable. That's why this course should be called electromagnetism, right? But back then, that was the first indication that these two worlds are connected. Of course, they didn't know how deeply they're connected. And as a result, it triggered tons of research. Tons of bright minds dived into that, like an Ampere, Faraday, then later on Maxwell, and so on. And they discovered tons of important stuff, which we use now and sounds trivial for us. And this simple experiment triggered that all. Right? Okay, so I felt like it should be mentioned, right? The importance of this Oersted experiment. And now the major point of today's class, right? So, magnetic force. So what do we have at this point? At this point, we know two ways of finding magnetic field, right? So we can use Biot-Savart law to find magnetic field, or we can use Ampere's law. They're both equally strong. They're both fundamental. You can apply them basically at any point of the universe at any moment of time. No restrictions, right? And now what is still missing in our foundation of the magnetism? Very, very important element of the foundation. Let's compare with the world of electricity, because lots of similarities between these two worlds. In the world of electricity, again, we had two ways of finding electric field. Coulomb's law, first option, and then Gauss's law, right? And then, in order to complete the foundation of electricity, what else did we introduce? We introduced the electric force. Why do we need electric force? Because we need to describe how do these electric fields interact with the material. And of course, any material consists of gazillion number of charged particles. If you know how these fields interact with a charged particle, then you should be able to describe interactions of magnetic or electric fields with any object. So we added electric force. So these ways of finding electric field plus electric force, that's basically the foundation of the electricity. And now there must be very similar situation in the world of magnetism. So now we know how we can find magnetic fields, but now we need to introduce the formula which would describe interactions of this field with a material, with any material. Again, inside of the material, there are tons of charges, point charges. So now we need to introduce the fundamental equation. A magnetic force on a point charge. If you know that formula, you should be able to describe interactions of the magnetic fields with any object. But of course, you'll have to apply some logic in order to make a transition from a point charge to a some bulky material, right? So let's introduce the magnetic force. So first, we're going to introduce magnetic force acting on a point charge. Right? This is the fundamental equation, one of the fundamental equations. It creates, together with these formulas, right, to how we can find magnetic field, plus this, it's a foundation of magnetism. In a couple of weeks, we will introduce, we will sort of present the set of Maxwell's equations. And this equation is not a part of Maxwell's equations, but it will be added to complete a foundation of electromagnetism. So this formula is one of the most important formulas in physics. Right? The same like electric force. You remember F equals Q times E? It's one of the most fundamental equations in physics overall. And this one. Okay, then we're also going to present the magnetic force on a current. This is not fundamental equation. It's basically simple. This can be simply derived from this one. So that is fundamental, and that is very practical, because in our life we have tons of currents everywhere, right, in our experiments, in our devices, and they're exposed to the magnetic fields, right? So this is very useful, but again, it's not fundamental. This is fundamental because this can be easily derived from this. Right? So, but anyway, we will have to present this one and that as well. So let's start with the magnetic force acting on a point charge. The title slide, and so let's assume that we have some point charge Q, and let's assume positive for simplicity, which moves with velocity v that way, and let's say it is exposed to some magnetic field. Now let's say at this moment, at this point, magnetic field points that way. And this formula, which we're going to introduce, again, it's so fundamental that it cannot be derived. It just basically, it was basically written based on observations. Based on observations. Any foundation of any theoretical physics usually written based on observations. And the same here. Right? You remember, like Gauss's law, Biot-Savart law, again, they cannot be derived, they were just written based on observations. And the same here. Okay, so what can I do? I can say, okay, here is the formula. F, force on a point charge, equals to charge. Hello? Is something wrong? No? Okay, and times the cross product between the velocity and the magnetic field. Okay, first of all, you remember at the very beginning when we started introducing magnetism, I told you that in the world of magnetism, everything is in dynamics. What did I mean by that? So, in order for a charge to produce magnetic field, it must move. Stationary charge cannot produce magnetic field, so it must move. And now, in order for a charge to experience magnetic force, it also has to move. You see velocity. If you have magnetic field and stationary charge, this charge is not going to experience any magnetic force. So you see, there must be some dynamics. There must be motion. Charge must be all the time to be in motion in order to either produce the magnetic field or in order to experience a force from the magnetic field, right? So you see what is interesting about this formula, that there is a velocity in this formula, velocity of a charge. So cross product between velocity and the magnetic field and the charge. So now, you see again, cross product, right-hand rule number 1, we have to use. Right? So if you want to find the absolute value of the force, of course, it will be just Q times V times B and sine of angle between these two vectors. Direction can be found using the right-hand rule, but you have to be careful. It's not a complete story. Direction, if you find the direction of this cross product, V cross B, right? So that's the first step. Then after that, you have to check the sign of the charge. If your charge is positive, then yes, direction of V cross B gives you direction of the magnetic force. But if charge is negative, then this direction must be flipped in order to find direction of the force. Be careful, right? I will keep reminding about this, right? The same like with the electric force. It's sensitive to the sign of the charge. Right? So careful again. First find the direction of the cross product and then quickly check the sign of the charge. If it's positive, that direction gives you direction of the magnetic force. If charge is negative, that direction must be flipped. Okay, and now back to this example, right? So let's find the direction of the magnetic force in this case, right? This angle alpha, it's here, right? These two vectors, V and B, of course, we can introduce this plane, right? So this plane is formed by these two vectors. And now, so what will be a direction of the magnetic force acting on this charge? V cross B, again, you remember how to apply right-hand rule. Sort of align your right hand, along the direction of the first vector in the cross product, along V. Then orient it in such a way so that you can bend your fingers in the direction of the second vector B. B is that way, so I have to position like this, right? And my outstretched thumb gives me direction of the cross product. So in this case, its cross product is up, V cross B, and since the charge is positive, so that direction is the correct direction for the magnetic force. Right? So direction of the force is up. As I told you, couple of classes ago, from now on, most of the equations are going to have cross product, and you have to be very, very comfortable with the right-hand rule. Otherwise, you will struggle, especially on the final exam, and the second also. So now let's look at a few examples. Right, so let's look at this case. So magnetic field, you see uniform magnetic field, and charge flies, positive charge flies along the magnetic field lines. It's like if you take a solenoid, right, and send a particle along the axis of the solenoid. So in this case, charge will fly along magnetic field lines. So what will be the direction of the force? In this case, since velocity is parallel to the magnetic field, what's the angle between them? 0 degrees, right? And as a result, cross product, where there is a sign of angle, sine of 0 degrees is 0. So in this case, the force is 0, right? So if you send a particle along or in the opposite direction to the direction of the magnetic field lines, your particle is not going to experience magnetic force. So if you send a particle along the axis of the solenoid, it will just move straight without changing its direction or changing its velocity, because the force in this case, magnetic force, is 0. Right? Okay, so we remember this. Right, so now let's send the particle perpendicular. So that if you send the particle perpendicular to the solenoid, let's assume that there is a hole somewhere. So in this case, yeah, of course, the magnetic force is not going to be 0. So how can we find the direction? Again, the right-hand rule. So first, V is up, right? So V is up. Again, I'm confused about directions because the screen is, on the screen, everything is flipped. All right, so you need to first align your hand along the direction of the velocity, and then orient it so that you can bend your fingers in the direction of the magnetic field lines, right? In this case, right, so it will be V cross B. Right. Everything is flipped for me, right? So that's why I'm standing, right, completely confused, right? Not completely, right? Right, so it will be into the page, right? V cross B. Okay, yes. So if it's towards you, it will be into the page, into the board for me, right? Okay, so, all right. So then, next example. This B is into the board, right? And velocity is that way. So what's the cross product, direction of the cross product? Again, V, then B is into the page, into the board. So I have to position my hand like this. So V cross B, and my thumb gives me direction which is up. Right. Again, it's a V cross B, and then check the sign of the charge. Charge is positive, so this direction is the correct direction for the force. So force will be up. Right. Okay, and now the last example. Let's assume this situation. So basically, it's similar to this, but now charge is negative. Right. Again, V cross B. Right. So you see cross B. And my outstretched thumb gives me direction of the cross product, V cross B. But the next charge is negative now. Charge is negative. So I have to flip the direction. So now direction of the force is negative. Right? Be careful. All right, on the exam, second midterm or final, sometimes I give, okay, not on, this is not going to be on the second midterm exam, so it will be on the final exam. Very often I give situations like this, and quite some students, not many, but a few students forget to change the direction, right? Because the charge is negative and you have to adjust the direction of the cross product. Right? So now next will be a question for you. Let's imagine this situation. So you see, now we have permanent magnet. Magnetic field lines are given, you see them. And a positive charge flies straight up. The pole is in your chat. I can see it, right? It's right in front of me. Right, so you should be able to see it as well. So what will be direction of the magnetic force acting on this positive charge? In this case, it's actually a proton, right? So direction of the magnetic force. And what? 5 options. right, left, in, out, and 0. Right. Can you try it? Okay, I see you started already answering. And again, if you're still not comfortable with a right-hand rule, although you already used it in Physics 1, right, and now in Physics 2, so come to the office hours, right, and I can work with you. So it's actually today from 2 to 3. How come that there is another option at the end, other? What is that? I didn't see that. Um, okay, so I see most of you picked option D. Okay, it should be enough. Yeah, it looks like you finished. Okay, let's just quickly run it. Again, first cross product, V cross B. So V is up, B is that way, right? Again, directions, confused with the directions. All right, so V cross B, all right, so V cross B. So it will be for you out of the screen, out of the screen. Those of you who picked D, yeah, that's the correct. And since the charge is positive, so the direction of the cross product gives us direction of the magnetic force. Okay, so it looks like most of you are comfortable with using the right-hand rule. So this, I'm not going to poll it, all right? So in this case, similar situation, but now charge flies at this point. So it flies. So let's find the direction of the, or some information about the magnetic force. So in this case, magnetic field is that way, right? And these two vectors are anti-parallel. They are in the opposite directions. So what's the cross product of two anti-parallel vectors? 0 degrees, because the angle between them is 180 degrees, right? So you see, so this way, this way, and then this way. So 180 degrees. Sine of 180 degrees, sine of pi is 0. So the cross product is 0, so the force is 0. So in this case, yeah, particle is not going to experience magnetic force. Okay, so now, so that was what the equation, this equation which we just presented. Yeah, this is one of the fundamental equations in physics, right? Which forms the foundation. It's part of the foundation of magnetism. And so the next equation, it's not part of the foundation. It's very important from the practical point of view, but it's not part of the foundation because it can be easily derived from this equation. Right? We're not going to do it because it's mainly like calculus, a little bit of calculus. So magnetic force on a current. So now we have basically a bunch of charges traveling in the same direction with the same speed on average. Right? and we'll just present the formulas. So let's assume that we have a completely arbitrary wire with current. Right. Current I. And it is exposed to magnetic field. It doesn't have to be uniform in this case. And again, as I said, this formula which we're going to present can be derived from this one. Right? And actually, the structure of the formulas are very similar. We just need to replace a few quantities. Can you guess? Charge must be replaced with what in order to have the formula for a wire with current? Most likely, if you think, right, it should be, instead of a charge, we should have current, right? Current, I. But instead of velocity, we should have a different quantity, but that's different, more difficult to imagine. Okay, instead of velocity, we need to introduce the vector dl, which is an element, infinitesimally small element of the wire. All right, so this is dl. And now I have to, at this point, every time I feel very uncomfortable, I have to apologize on behalf of the author of this book, because up to this point, every time Randall Knight, used ds to denote infinitesimally short elements of the wire or a loop, right, or whatever. And now suddenly he started using dl. It shouldn't be like this in the book. If you use the same certain notation, you have to use it throughout the whole book. Switching notations, it doesn't sound cool. It doesn't look cool, right? And the way how I explain it, right, because it's just bizarre. Right? There are classic books, right, physics, like Giancoli. And there are some other authors which, I don't know, write their own books, publish, right? And in order to be different, I don't know, they very often try to use just different notations. But in this formula, which we're discussing, in this formula, it's sort of like an unwritten convention. Sort of in the whole world, you can open any book and everywhere DL will be used, not DS, DL. And so he probably didn't feel comfortable using here DS, so he also switched to DL. Right? It's not a big deal, it's not a crime, but it doesn't sound good, right? It doesn't sound cool, right? So guys, so you remember, so DL, it's an element of the wire. Although up to this point, the author used DS all the time. Right? It doesn't happen often in the books. Usually, if there is a certain notation, it will be used throughout the whole book. Right? Okay, so DL, element of the wire. Right, so that's the formula. So now that's the force acting on this small section of the wire, right, equals the value of the current, then dl, and you see dl is the vector. And what determines direction of this vector dl? Current. Current determines direction of this vector dl. Right? And then again, cross product, right-hand rule, number one. Right? Cross it, so dl must be crossed with b. Cross product between dl and b. Right? Again, as I said, it's a very important formula, but it's not fundamental. Fundamental, the previous one. Okay, this one. Right? Because this can be easily derived. Okay, all right, so, but we're not going to use this formula. I think most of the time we're going to use if you apply this formula for a straight wire, right, for a straight wire, if you apply this formula for a straight wire of length some L, right, length L is exposed to the magnetic field, right, for example, like this. Let's say you have this straight wire, so now you don't have a bent wire, straight wire with current I. Right. And you can easily move from this formula to the formula for this case. So it will be, again, it's exposed to the magnetic field, right? So the formula will be just exactly the same, but now you just don't have D's. So you have F, I, L, cross B. Right. So that's what we are going to use most of the time in this course. Right? Because here you have to use integration and, yeah. We try to stay away from integration, although not all the time, right? So this And that's what we are going to use in our recitation classes, right? So for some of you tomorrow, and for some of you on Thursday. Right? Yeah.
I just had a quick question. What does length times B give you?
What do you mean in terms of units? Okay, L cross B doesn't give you anything, right? So if you also multiply by the current, it gives you the force.
Okay.
But L cross B, I don't see any significance in this cross product. Of course, it gives us a direction of the force. Yeah, that's what it gives. And that's what it determines. Right? Because current all the time positive, current, the value of the current cannot be negative. So in this case, direction of F is determined by the direction of this cross product L cross B. In this case, every time we had to take a cross product and then look at the charge. Do we have to adjust the direction or not? But in this case, L cross B determines the direction. But physical meaning, I don't see any physical meaning of that cross product by itself. But if you multiply by the current, yeah, it gives the force.
Okay.
Mm-hmm. Okay. Right. So now a couple of examples, right? And this case. So you see magnetic field is straight up, uniform. Maybe it's inside of a solenoid. And wire goes up. I mean, the wire is vertical and current flows up. So what is direction of the magnetic force? Again, you remember, we need to take a cross product. Again, it's the second formula, right? So for a straight wire. So value of the current and L cross B. So let's look. And again, direction of L is determined by the direction of the current. Right? Direction of L, it's the direction of the current. So L cross B, so I is up, so it means that L is up, vector L. So L up. B is also up. So cross product of two parallel vectors is 0. I started applying right-hand rule and then I realized, okay, this is the trivial case. So if you have two vectors parallel to each other or anti-parallel, the cross product all the time 0. Because the angle between, in this case, is 0, like that's what we have here. Sine of 0 degrees is 0, so magnetic force is 0. So in this case, this current, this wire with current is not going to experience magnetic force. So in this case, no force. Right. So, but if we turn this magnetic field by 90 degrees, like in this case, so basically the same situation, but now magnetic field is into the board. So now, yeah, magnetic field is not going to be 0, so we have to be careful and apply right-hand rule properly. So again, L is up, B is into the board, so right-hand rule, so up, cross B. So as a result, my thumb gives me direction of the magnetic force that way, right, to your left. Right. Left. Still, all right. Okay, so so the wire will be slightly bent. So that's what we need to know about the magnetic force. So now let's just again sort of summarize. So in the world of electricity, we had two, basically these are foundations. So in the world of electricity, we had two ways of finding electric field. Coulomb's law or Gauss's law, and then electric force, F equals QE. That is foundation of electricity. Now foundation of magnetism. Foundation of magnetism up to this line. So what we have above that, it's a foundation of magnetism, right? So you can find magnetic field using Biot-Savart law or Ampere's law. And then this formula describes how we can describe interactions of the magnetic field with charge. And then, of course, you can, using some logic, some arguments, you can extend it and describe how these fields interact with materials, because any material consists of point charges, right? Inside of any material, gazillion of point charges. And again, this formula, yeah, that's basically very practical, very useful, right? So, but this is not the foundation of magnetism, right? But of course, in our life, in our experiments, research, of course, this is used a lot. Right? And so now, all right, let's look at some applications of these magnetic forces and applications using of this, our fundamental formula. F equals Q V cross B, right? And we're going to introduce the cyclotron motion. Okay, we still have a few minutes. At least I will be able to, sorry, I will be able to start. So it will lead us to an amazing and a beautiful phenomena. Just recently I watched one documentary about one guy chasing that phenomena. Right? But anyway, so if you have point charge, and if you send it along magnetic field lines, like parallel to the axis of the solenoid. In this case, we just discussed a couple of slides ago. Of course, in that case, charge is not going to experience any force, magnetic force, of course. Right? And of course, it will move straight along a straight line with the same velocity forever and ever. So that is kind of boring case, nothing interesting. But let's turn everything by 90 degrees and send a particle perpendicular to the magnetic field. And let's discuss that in details. Again, as I said, if you send a particle, charged particle, along magnetic field lines, nothing interesting. It's kind of boring. But if you send perpendicular, then it will lead us to very important processes. Right? Okay, so let's imagine we have this uniform magnetic field, which is into the board, B. And as I said, now let's send particle, a charged particle, perpendicular to this magnetic field. So it must be in this plane, okay, in this plane, right? So let's imagine this is our point charge, positive point charge, and it flies this way. So what are we going to get? Which trajectory? So in order to understand what happens, right, of course, we need to first realize what's the direction of the magnetic force. Right? Because a magnetic force is going to change, is going to do something with the trajectory of this particle. Because if we did not have magnetic field, of course, this charge will just fly straight along a straight line with the same velocity forever and ever, according to the Newton's first law. But now we have magnetic field, of course, it is going to experience magnetic force. What's the direction of the magnetic force, which is going to change trajectory of this particle? Direction of the magnetic force, again, you need to align your hand along, right hand, along the direction of the velocity, so V, then cross it with B. B is into the page, into the board, so V cross B, and as a result, your thumb gives you direction of the magnetic force. So it will be that way. Okay, let me show it here. So that's the direction of the magnetic force. Again, I just used that formula. And charge is positive, I assumed for simplicity. So direction of the V cross B gives me direction of the force. Okay, so now, if there is a force, of course, force changes, do something, changes velocity. Why? Because according to the Newton's second law, F equals ma. If there is a force, there must be an acceleration. And if there is an acceleration, we all know that acceleration describes changes in the velocity, right? Acceleration describes changes in the velocity, physics 1. So it means that force changes velocity. So what does this force change in this velocity? Velocity is a vector, has two parts, magnitude, direction, right? And we have force, which tries to change that velocity. So what does this force change in the velocity? Does it change its magnitude? Its magnitude, magnitude of the velocity. So force X, does it change magnitude of this velocity? No way. because it acts perpendicular to the direction of motion, perpendicular to the velocity, direction of the velocity. So if force acts perpendicular, it cannot change direction. It cannot change the magnitude of the velocity. So magnitude of this velocity is going to be the same. So speed of the particle is going to be the same. So it looks like we're going to have. Okay, that's just a second. It just indicates the class is over, right? So let me just quickly, half a minute. So it doesn't change the magnitude of the velocity, but what it changes when it acts perpendicular, it changes direction. It's sort of like this force yanks on that velocity, and as a result, velocity changes its direction. First, it points this way. Then, after infinitesimally short period of time, it moves slightly, it changes direction of the velocity that way, then this way, this way, this way, and so on. So, and all the time, force is perpendicular to the velocity. So, this force, changes direction of the velocity. So, does this remind you anything from Physics 1? You've seen similar process, similar motions in Physics 1. If you recall, motion of satellite around the Earth in the presence, of course, in the presence of the gravitational force. It's exactly this situation, but of course, instead of magnetic force, you had back then gravitational force, force of gravity that Earth exerted on the satellite. Again, that force was perpendicular to the direction of velocity. That force, again, couldn't change the magnitude of the velocity. What it could change, that force, only direction of that velocity. As a result, we had which motion? With circular motion around the Earth. Now we're going to have circular motion in this magnetic field, right? So, and every time force is perpendicular to this trajectory, right? So if a particle is over here, velocity this way, but still force all the time perpendicular, because force is perpendicular to both of these vectors, v and b, right? And here the same. So this motion is called the cyclotron motion. So the next class, next week, because next class is an exam, we're going to describe this motion, this cyclotron motion, right? Start describing it. So we'll get the radius of the cyclotron motion, period of cyclotron motion, all right, and some phenomena which keeps us alive on the face of the Earth, right? Without that process, we would be all dead, right? Okay, guys, thank you. Sorry for holding you extra minute. All right, I will see you on Thursday on the exam.
Day belongs to them, the women and the men, the athletes standing proud and tall. The triumph and the tears, the sacrifice of years, they come today to